In this video, we will discuss two numerical examples related to single area power system, automatic generation control. So the question is written here. A power system has a total load of 1400 megawatt at 50 hertz and the load damping constant is 1.2 per unit. A load of 50 megawatt is tripped. Find the steady state frequency deviation if there is no speed control. There are two cases: if there is no speed control and if there is a speed governor. With a spinning reserve of 250 megawatt, the system has a spinning reserve of 250 megawatt and a regulation of 4% on this capacity. Due to governor deadband, only 75% of the governors respond to this change in load. So let us go through the solution. So the total load was 1400 megawatt and a load of 50 megawatt is tripped. So the total load after tripping is 1400 minus 50. So it is 1350 megawatt. So then the D value, load damping constant for this particular load, active load, is 1.2% of the load for 1% change in frequency. D equal to 1.2 means 1.2% change in load for 1% change in frequency. So 1.2% of load, that is 1350 divided by 1% of nominal frequency 50. So we will get 32.4 megawatt per hertz. That is the value of D. So when there is no speed control, the frequency deviation is directly given by load change divided by load damping constant with a negative sign. So now here load is tripped. There's a decrease in load. So decrease in load is indicated by negative sign. Delta PL is positive for increase in load and delta PL is negative for decrease in load. So there is already a negative sign here. Then this load decreases minus 50. Okay, so this will become positive. So this is 1.543 hertz. You can cross check like this. When load decreases, frequency has to increase. Okay, so when load decreases, delta F has to be positive. So the steady state frequency will be nominal frequency plus this delta F. So it will be 51.543 hertz. Now the second scenario, when there is a spinning reserve as well as speed governor. So the total generation including the spinning reserve is 1400 megawatt plus 250. So it is 1650 megawatt. And 75% of this will respond to the load change, because only 75% of the governors will respond. That is given in the question. The governors, only 75% of the governors are going to respond. So 75% of this total generation capacity is 1237.5 megawatt. So that is the total generation. So regulation of the speed governor is given as 4%. So the speed droop coefficient, the reciprocal of speed droop coefficient 1 by R is equal to delta PG by delta F. Delta PG, that load total capacity of the generation capacity which will respond to load changes 1237.5 divided by 4% change in nominal frequency. So it is 618.75. This is the value of 1 by R, because you know from the characteristics delta F and this is power output. Okay, so this is the graph and this slope is 1 by R. So for 1237.5 megawatt change in power, the frequency changes 4% of 50 hertz. So that is delta Y by delta X will be R. So 1 by R will be reciprocal of that. That is this change in power divided by change in frequency. That is 618.75 megawatt per hertz. Then the stiffness factor beta, or that bias factor beta, is 1 by R plus D. 618.75 plus the value of D, 32.4. So we will get 651.15 megawatt per hertz. So steady state frequency deviation is load change, negative of load change divided by beta. So it will come around 0.07678 hertz. So you can see that the frequency deviation has reduced because of governor action. Previously it was 1.5 hertz change in frequency. Now it is only 0.07678 hertz. Now coming to the second example, here the data of a single control area is given. The total generation capacity is 2000 megawatt. Normal load is 1500 megawatt. Inertia constant of the generator is 4.8 second. Damping constant, load damping constant is 1.2 percentage. Frequency is 50 hertz. The speed droop coefficient is R equal to speed governor parameter R is 2.5 hertz per unit megawatt. So please be careful with this unit, hertz per unit megawatt. Now there are some questions. Calculate the parameters of the automatic load frequency control. Then for an increase of 0.02 per unit in load, find the steady state frequency change without the governor control, then with governor control, then in the last case with governor control but without any frequency sensitive load. Frequency dependence of loads neglected. So we will do it one by one. So D is given as 1.2. So 1.2 percentage of total load 1500 divided by 1 percentage of nominal frequency. That is the meaning of D. D equal to 1.2 means 1.2 percentage change in load for 1 percentage change in frequency. So it is 36 megawatt per hertz. But this R is given in hertz per unit megawatt. So we have to get the value D in per unit megawatt instead of megawatt. So you can divide this by the base power. Here the generation capacity is 2000 megawatt. So we will divide this by divide this by 2000. (36) divided by 2000. So we will get 0.018 per unit megawatt per hertz. So the generator is 1 by 2hs plus D. Generator model is 1 by 2hs plus D. So 1 divided by 2 into h is 4.8, D is 0.018. Okay. So this is the parameters of automatic load frequency control. If you want to calculate the time constant of the power system, you can represent this in Kps by 1 plus STP form by dividing numerator and denominator by the 0.018. Okay, we will leave it like this. Then without governor, the speed deviation is frequency deviation is minus delta PL by D. Minus delta PL is minus of load change 0.02 divided by D value is 0.018. So minus 1.11 hertz is the change in frequency for without governor. Then with governor you will get a 1 by R in the denominator. So R value is 2.5 per unit megawatt per hertz. So substitute that, you will get the frequency deviation. Then in the last case, frequency dependence of loads is neglected. So D is 0. When frequency dependence is neglected, D will become 0. So only 1 by R will be there in the denominator. You can get the value of frequency deviation. Okay, so we'll stop here. Thank you.